Good morning, everyone. Thank you for coming this very morning. I know it's very early, but let's start off our presentation. Our presentation is about ISS, Industrial Simulator. My name is David.
I'm Lexi.
And my name is Elena.
So before we dive into our actual project, we want to give a special shout out to Max Powers and Yulin for helping us hardware and software problems. And this is a brief list of what we're going to talk about, and let's dive into problem statement.
So the problem that we identified is that there is a significant gap between human-machine systems designed for large-scale industrial applications and simulations for educational purposes. We aim to create a solution that is adaptable, scalable, and also expandable. So the product that we came up with to solve this problem, or the solution that we came up with to solve this problem, is the Industrial Systems Simulator, or the ISS. And this serves as an accessible tool for students who wish to learn more about topics involving production, simulation, manufacturing, and modeling. So really quick, we'll go into a demonstration.
Sorry, there's no audio because we're laughing hard in the background. But briefly, this is our demonstration video. Just wanted to show you guys how this is working with our system on the computer as well. So on the left side, there's a terminal open, and then it's currently processing one product order. And if we skip forward, because we wanted to use a human machine system, there's a human part inside of this whole simulator as well. After producing final product, it will move into the pass bin if it's correct. And on the left side, as you can see, it provides a result.
So over here is a brief layout of what you just saw, and on the top are some pieces of equipment that we just used that we'll dive into in a second.
Sorry about that.
So starting off is a sorting machine. There's 3 different products, product A, B, and C. For A, the red and the green pieces will be circles. For B, they'll be ovals. And for product C, it'll be squares. And each product consists of 5 parts. So each of these 5 parts are manually put into the respective bins of the sorting machine.
So next we're moving on to robot 1. As you saw in the video, this robot's responsible for interacting with the sorting machine. So it picks up each part of the assembly and places them individually onto conveyor belt number 1 to be sent over to the next robot. So this is controlled through Python script, which utilizes the Pinerio 2 package with commands to execute joint coordinates as well as the control for the conveyor. After this, robot 2 is responsible for picking up these pieces off of the conveyor belt and placing them in their respective spot in the assembly plate, where the human will then finalize the assembly by, as you saw in the video, hitting it closed and flipping it over.
So once the human flips over the part, the second robot will pick it up and then place it onto the second conveyor belt where it'll move underneath the camera. And this leads us to the quality control section. So the goal of the quality control is to verify the color placement of the final products. So the goal is to have the red on the top left and the green on the top right. And the camera is placed over conveyor 2, and we use OpenCV and NumPy. And the color detection will verify the assigned colors in the regions of the frame. And once it processes that, it'll move the conveyor accordingly. So if it processes it as a correct assembly, then it'll move to the green bin. And if it's incorrect, it'll move to the red bin. And also, once this is done, an image will be taken and uploaded into files.
So how do we control all of that using one system? Anyone remember our main keywords? Any one of them, maybe? Well, yes. The main key point? Yes. Expandable, right. So we want to make this industrial system simulator more expandable, more manageable, and easy to modify. So how we achieve that is actually we created one master script and 3 different product assembly scripts in order for us to manage better, because each one has about 200 lines of code, and it will be hard to manage when we put all of them into one single script. That's an example. And inside one of the main script, there will be class. We're using classification to define all of the necessary details of the code. For example, setup, disconnect, quality control, and executing the sequence. And in the end, the user will input any order number or sequence, and it will execute through that order. And this is an example that we saw in the earlier video where it gives out the specific results for one product. For example, this shows that the robots are connected, setting up, and then finalizing the quality control here, and then saving the image at the end and disconnecting for a clean process. To test and validate our scalability, we made a user guide to make sure that anyone who tries to use ISS is able to create a new product and manage our new system. In this example, I actually had to ask one of my housemate if he can create a new product. It's called D, and he was able to manage that just following the user guide that we provided, and all the files above will be provided if you use ISS with us. So, we here spent a lot of time learning about courses and different engineering, but we haven't had an actual like factory assembly hands-on experience. So for students, it will be a valuable tool for us to use, have more experiences throughout the assembly lines and factories. And for the industry people, they can really use this to model their new setups or find debugging errors about their existing assembly factories. This is our future step, just briefly mentioning that we could develop more on a sorting machine, add additional products, and use parallelization. We can use parallelization to make it more effective and faster using multiprocessing or threading as well. And that is the end of our presentation. Thank you. Yes. Yes, so if it's possible, we would like to incorporate in one of the classes. Dr. Randy is currently teaching quality engineering, and we actually did their project using our ISS, doing time study and comparing the time results. We could definitely use this in all of the courses that combines all the production, simulation, and manufacturing. And if we open all the files to students, they could figure it out, and you follow the user guide, it will be very easy to modify however they want.
We volunteered. I would say that we definitely studied, principles of the assembly line. So we studied not only like the time study, but the ergonomics of an assembly line, as well as the other factors such as like the programming for these types of robots. I'm not sure if I'm answering your question here, but I think that this really just wrapped it all together, and really just was a summation of my education as an ISE, and that's why I think it'd be a very great teaching tool. Does that answer your question? Yes. Yes. So we did some hands-on. I remember specifically we had work design lab where we were doing time studies. We were folding paper airplanes and identifying bottlenecks in the process, which that was some really good hands-on experience. And obviously it was very memorable because that was 2 years ago. But I feel like since then there wasn't anything super, super technical. So I feel like this would be a great teaching tool to kind of, up the standard.
Hi, we're group 2, and we are Piscardia. I'm Max Sharconi.
I'm Joy Edwards.
And I'm Jim Polomano.
Before we start, we'd like to give a special thanks to Alex Sawatsky, Yulin Lee, and Max Powers for their assistance on our project. So let's get into it. So small-scale farmers lack effective tools for monitoring and diagnosing crop health. A better solution is needed to avoid misdiagnosis, delays, and eventually crop losses. Pescardia offers video-based diagnostics, which helps farmers make accurate assessments and informed decisions in protecting their crops. So, what is Pescardia? Pescardia is not just a robot. It's a mobile platform designed to help farmers monitor and diagnose their crops. Some of the key features of Pescardia are video analysis. So essentially, Pescardia takes a video of your crops, it's run through our machine learning model, and then it is assessed once it's ran through the model. Next, it offers pest and disease detection. So there's 3 main categories with Pescardia: bacterial, fungal, and healthy. And they all offer actionable insights depending on how your crop is categorized. Next, it's all-terrain. Pescardia is built for reliable performance across diverse farm environments. And lastly, it's remote controlled, making it easy for any farmer of any experience level to use it.
Here you can see our robot in action as it's driving through the Rutgers Gardens rows while it's identifying the crops.
So the value prop. It's time-saving and user-friendly. So it reduces the labor intensity with an easy-to-use system that automates key parts of the crop monitoring process. It's reliable and offers accurate diagnosis. It provides accurate machine learning-powered analysis of crop health, eliminating the human error that may come with manual field inspection. And lastly, it's adaptable. Pescardia is built for various crop types and farm layouts, making it a flexible and scalable solution for different farm environments.
So for methodology, we have 2 key factors. We have manual navigation, which is basically all the signals are sent from a remote control. Then there are process, which is that causes the robot to go through the field on user input.
For the image recognition, we have our camera connected to a Raspberry Pi, which will record the crops while driven through the rows. Next, once the video is complete, it will be put into our pre-trained model where it'll identify the crop and the condition. And lastly, the output will display the condition of the crop, where exactly it saw it, and what you may do to treat it. A little more about our pre-trained model. We use YOLO5, a CNN convolutional neural network, which basically it's a real-time object detection model, which we use by inputting annotated image data sets so it knows what exactly its targeted objects are. The first part is the backbone, where it collects the low-level features and high-level features. These include the edges, the corners, and all the shapes of the object. Next, it goes into the neck, the neck part, where it combines all of these features together, so it's able to determine the object no matter the size. And lastly, it's the head, where it makes its final prediction and tells you the confidence score. Testing validation. All right, so when we went to the farm, they didn't have any fungal or bacterial disease plants, so we were only able to test that with healthy. But when we did our tests, we were able to find that 85% of the predictions were accurate. And then out of that 85%, the average confidence score was 55%, which is in the ballpark, which is like it's known for that to be good prediction. And also take into the fact that the other data sets, like with fungal and bacterial lettuce, is that they're very similar, and the only difference is like the coloration. So we consider this to be a very decent confidence score.
So for our system integration, we have two parts, of course, software and hardware. For software, we use a couple packages, such as YOLO v5, as explained by him, OpenCV, and PyTorch. This is all run in different interfaces, which one is Arduino, which is Python-based, and the Tony interface, which is Linux-based. And for hardware, we actually have a lot of components that made this, but we're just going to focus on the most important ones that are the camera itself, that is for image recognition, the Raspberry Pi that processes all the pictures that it takes, and the Arduino Mega, which is the main controller for the robot to move through the field. So for innovation and contribution, we have three key factors. Video-based cell diagnosis, empowering small-scale farmers, and versatility. This is we wanted to keep it pretty simple. So for the first one, it captures a video of the crop, then it goes for detailed analysis, then it tells you if it's healthy, fungal, or bacterial. Then we move to those empowering small-scale farmers. This is what we aimed to with this project, it was to be like really simple for farmers that are not really technological based, and then for versatility, it's our robot goes as tested in the video and in the farm. It's to be all terrain, and yes. So for future outlooks, we just wanted to keep two main future steps. The first one being live streaming, which means that as it goes is live streaming and it's being recorded. And the second one, it'll be for the robot to be fully autonomous. And that's it.
So as I watched, I mean, I love the artsy looking robot going along. I mean, clearly, if you were to sort of proceed down this path, as you said, either self-control, but have you thought about maybe like incorporating a GPS? So, for example, creating a map of the farm and then you could integrate like a GPS module onto the robot to allow it to, now follow.
So we were trying to make that happen. We actually wanted to make that happen because it's like so much stuff took our time on this. We were planning to apply sensors like such as I think the GPS module and different sensors that actually goes through the crop and like it knows where the car is and where the image was taken from the thing. So yeah, we wanted to do that.
Also, like for now, right now, like you have the video when it's input, like it shows you. So now we have like a timestamp of when exactly it detected the fungal or bacterial disease. So like I'll let you know where to go back into the video and like further inspect it properly. The training data. So basically, we took a bunch of lettuce crops, and then we separated them into different categories: healthy, bacterial, fungal. And so we just annotated we just boxed each object, and then we ran it through the model, and then it was able to detect it, split it up.
Does your model have any inconsistencies determining if it was actually lettuce or?
So for the purpose of the project, we only based our project on lettuce. We didn't do anything else besides lettuce or any other crops.
What? It's one of the more faster models, and it's also more efficient. Yeah, I mean, we were planning on using the TF Lite model in a Raspberry Pi, but the frame rate was so slow that it didn't seem efficient.
And what is your output by the entire population that you've sampled, or is it by individual crop?
It's individual crop. I mean,
Individual and actual planting.
can you?
So you've got a row of lettuce with 10 lettuce heads.
Yeah.
Are you reporting by lettuce head, or are you reporting by the overall population?
Overall population.
What? But she said one thing. You said
No,
lettuce.
it's by lettuce head, so it goes by lettuce. It doesn't do the.
Yeah, but is your output showing that, or is it showing the overall health of the population?
Overall health of the
Yeah,
population.
the overall.
Gotcha. Thank you. Because if you were a farmer,
Yeah.
and you were actually running this, right, what you'd want to know is, assuming that fungal or things like that,
Yeah.
it's going to jump from plant to plant. So you want to find what portion of your
Yeah, no, that's why I timestamped it to find out exactly where it is.
Okay, so with the timestamp, you can go back and remediate.
Yeah.
Okay, gotcha. Good. Thank you.
Hi, good morning, everyone. We're Manuhand, and my name is Sabi,
My name is Brian.
My name is Anwar.
And we're Group 11.
and we're Group 11. So in terms of problem statement, being ISE students, we wanted to really focus on industrial robotics in manufacturing and assembly industries. And what I want to emphasize is for small-scale operations. So when we were doing our research, we found that there were two big challenges that were proving that industrial robotics can be inaccessible for really small-scale operations. One being that they require costly components, which can limit accessibility, and complex setups with interfaces that can really create challenges for users, especially for new users. And this can be challenging, as mentioned, for small-scale, low-precision tasks. So our pipeline enables the control of the robot nanohand, which you guys will be able to see in our slides, overcoming accessibility and complexity challenges in remote operations. So our solutions, I'll go right into it. So two main key points of our solutions is ease of accessibility, as mentioned. This requires just a simple Linux PC, USB or a web camera from your laptop, and a serial controller feeding into the robot nanohand. And the second key point is real-time control. This is all happening live, and it's really suitable for dynamic, non-repetitive tasks that require continuous input. One key example of this, you guys can see right here in the bottom pictures. For instance, you have a scenario where a low precision task needs to be done in a confined cell. Now, for traditional robotics, this might be a bit complex, but our solution, you have the camera in front of the Linux PC, and whatever hand gestures you make, the robot nanohand will replicate that. And that's all possible due to our nanohand pipeline, which enables that.
All right. Here in this demo, we'll showcase how our solution enable control the real time of robot nanohand. So first, here we see the users creating curling and uncurling their fingers. So the robot nanohand replicates this movement in real time. So next, the robot nanohand replicates the two fingers bench grip for assembly in real time. As shown here in this video.
So going into our software and hardware integration. So first, we input the hand into with the webcam. So the webcam looks at the hand, and then essentially after the webcam kind of looks at the hand goes through OpenCV, so it frames into it. And then the CNN model is from MediaPipe. We use MediaPipe to locate all 21 joints, and these joints are then later used to essentially map out the servos onto the robotic hand. And we'll show you that on how we do that. So with the CNN model from MediaPipe, essentially we get the part confidence map and the part affinity map. So the part confidence map gives us the individual joints, and the part affinity map connects the joints together. And with these, we use the Cartesian coordinates based on the pixels on the screen to locate where each joint is. And the reason why we do that is because we use the top joint on the tip of the fingers with the joint closest to the palm, and this joint essentially acts as our input. So then we calculate the distance between these joints to see whether or not they're curled, and then we normalize this curling into 0 to 1 so that our servo moves based on the distance of the fingers, essentially. So if it's 0, it's fully curled. If it's 1, then it's fully extended.
Seems to our testing and validation, starting with first step for boost estimation CNN. Before they using Jitson Nano with TRT Bose hand CNN model, and this setup was slow and faced memory issue. So we switched and to an external connection with the MediaPipe hand tracking model in our laptops. So that's providing a smoother and fluid model for tracking the hand model. And in the second step for hardware testing, we begin to start the CCI camera, and it's and this setup was like give us poor quality image. So we start using the webcam camera or the USB cam camera, and give us like a good quality, a better quality image, as here shown in these pictures. And all setup like be in our in one, and all this entire system be in our one setup laptop. And the third step here for servo mapping algorithm, before we start using the joint angle measurement by mapping the servo robotics. Then we start use the Euclidean distance with a mapping servo to robotic action.
All right, so let's circle back on what we've accomplished. So with our pipeline, I want to emphasize that our pipeline enables real-time control of the robot nanohand specifically for low precision tasks aimed for small-scale operations. And what I want to emphasize, what our contributions is how we were able to achieve it is combining these three systems together. So first, you have the computer vision from OpenCV, then you have the post-estimation CNN model from MediaPipe, and then you have our servo actuation mapping script. So all of those three systems are working together continuously to deliver that. And why is that important? Well, you have our value proposition. Number one key point is accessibility. This is all in a laptop setup, in a Linux-based laptop setup, where you have webcam, and the user is able to provide inputs, and the robot nanohand directly replicates that. Number two, safety. Well, how safety is because the robot nanohands, going back to that case where I talked about in a confined cell, the robot nanohand is doing the handling inside the confined cell, and the user is outside from it. And number three key point is also education. We've removed the Jetson Nano, the NVIDIA Jetson Nano, and since it's all in one laptop, it's designed to be a more buildable platform for future ISE students.
Thank you. We left that in the presentation, but they emphasized it, which is really important. Well done.
Thank you.
Thank you.
What's out there today? I mean, this is obviously has a lot of usability. What have you done some research in terms of how close is anything out there in the marketplace today?
Yeah, so when we were doing our research, we found that there's some stuff out there, but they require a lot more components, and they're not as accessible to, say, smaller scale operations where you need additional sensors. For instance, you might need a glove to put on, and you're adding just more components into your overall assembly. But this, you just have a web camera, and then you have your laptop, which is Linux-based, and it's feeding direct signals to control the nano hand. So that's where our innovation is.
Excellent, great job. And so is the nano hand commercially available?
Yeah, so it's an open source robot
Open
that
source
we're
robot.
using. Yep.
And the idea, though, at some point potentially, as you said, for a small scale, but especially in like hazardous sort of conditions, that someone would come up with a nano hand specifically made for hazardous, acidic, difficult environments,
Yeah.
things like that.
Yeah. And in terms of being buildable, our plan is maybe in the future, someone can maybe make a cobot. So instead of a hand,
Yeah.
you have your whole arm through that CNN model and being able to control from there.
Really nice work, guys. Yeah, nice.
Thank you.
Very nice.
Thank you.
Did you have any issues with required distances from webcam and backdrops and things like that?
Yeah.
You know, make sure there wasn't any issues with registering the hand and reading it.
Yeah, so some of the problems with depth, we did, for the normalization, we did have to experiment with different values for min and max values. So we did hard set a specific value for both.
Thank you.
Good morning, everyone. Welcome to our presentation. We are Group 12, and the name of our project is Pack. So let's get started. So we would like to give our special thanks to Dr. Farzad Yousefian and Yulin for their contributions. Our team consists of myself, Ali Arslan, Ankur Chaudhry, and Jeremy Hajel. So our problem, sorry. So this is our agenda that we'll be following. So our problem statement is that pack and outshare products waste space, increases cost, and takes too much time. In order to solve this, an automated system is planned to optimize space, reduce cost, and improve consistency in packing. Our initial goal is to optimally pack these odd shapes.
So as our project is very complex, we had to break it down in 3 steps. So our first phase was that we have to create a mathematical model. Our second phase is that we got to solve this linearly, and then our third phase is to solve it non-linearly, which is working with odd shapes. So the phase 1 is creating a mathematical model. This is where our majority of our time spent, because we have to make sure our mathematical model is correct and works. So what this basically, we worked with Dr. Yousefian to work with our model, where we came up with the objective function that is to minimize the maximum stacking height of all the objects in the packaging box. And there are certain constraints we have to make sure that they are all met, which one of them is a containment constraint, which makes sure all the objects are in that box and not outside the box. So we have to tell this to the model to follow. The model continued. We also have to make sure that we have another constraint that is called as a non-overlapping constraint. And what's happening here is that we have to make sure that if you have more than one object, they do not cut on each other and they don't overlap. For this, we have to make sure we use something called as a binary variable, where it gives the model a certain value, which is a 0, which means it's a false, and 1, that means a true. And what this means is basically it makes sure that the objects do not overlap and cut each other, essentially.
So we will move on to phase 2. Before we move on to phase 2, I would like to pay attention to some tools that we use. We use LiDAR scanning and also Groovy in phase 2. Let's move on to phase 2 now. In phase 2, we use linear optimization because nonlinear optimization is very impractical, so we first attempted linear optimization to find better solutions. In linear optimization, we first created our PaceMate objects and we LiDAR scanned them. In the LiDAR scans, we obtained the dimensions and the coordinates of these objects. Then we turned them into convex holes for getting them smallest convex shape that fully encloses a set of given points. Then we integrated these convex holes into our Groovy code, and our Groovy code gave us our optimal packaging layouts, as you can see in the last picture. To test and validate our results, we tested our math models layouts with our randomized layout. And in randomized layout, we obtained a packaging height that was very infeasible. Our math model decreased the height by 48.6%, the stacking height.
Okay, so next is phase 3. And phase 3 is where we incorporated our odd shapes. And we were recommended by Yulin to use a application called Blender, where we could physically simulate our model. And so on the left, you can see this is just a randomly placed object in the box, which you might see in industry right now. And then with our model on the right, you can see how we are able to use our nonlinear and incorporate that into Blender to show this. And then this is just a more specific example. You can see we reduced height by almost 50%. And then this is just some animation we did with our three different sizes, three different size boxes. You can see how we were able to do it on Blender.
So for our demonstration, what happens is that we have our objects that needs to be packaged, and this goes through our LiDAR scanning processing, which you can even use on an iPhone, which has a LiDAR scanning LiDAR scan, and then these inputs, the measurements you get from this LiDAR scan, are put into our convex hull code, where this then gives us the most optimal achieved layout for all the objects that you have. So for the value prop, why is it important? As we know that there's a lot of packaging waste produced over the years, and our whole goal is to enhance productivity, reduce warehouse costs, and of course optimize space usage. And for future direction, we think that there's a future for integrating this with the use of QR codes, where you can have a QR code for each object, which would directly have the measurements and the weight, etc., all these things, which can be scanned and then directly applied to the model. And another thing we could have, there's a future for, is using robots, where the robot can then, after you get the measurements and everything and all the layouts, the robots can be able to use to place all these in the packaging box. And a quick example we could apply this in the future is a U-Haul. What you could do is that, and this is just like a very vague example, where you have a U-Haul website. Customers can LiDAR scan from their phone all the objects and all the material they want to move out and find the best truck. This then inputs it into our model and gives the most closest or biggest or smallest truck size that they require and the most optimal way.
So for our contribution, as our model is very adaptable to the market today, and we were able to basically any sort of change, we were able to adapt to it, and it's just we were able to just maximize the space, which is, I think, also very important. Thank you.
So if I was in industry and I was running, I'm the CEO of Amazon, right? I got all these boxes going.
Is that really the
If I am, if I was. But you know, it seems to me, in terms of next steps or logic, I think you talked a little bit about it. So even if you put the QR codes, you quickly scan. Okay, I'm now going to get a map that's going to say this is the most efficient way. You know, the human interface with the machine is someone's now going to look at that map, figure it out. So it sounds like a next logical step would be sort of mechanized placement, so that you know, once you scan, you get the order. This is the pack. A robot or some machine assist, you know, rather than having that human interface of like, okay, here's the optimal pack. Because from an industry perspective, right, people are the most expensive things you have, right?
Exactly.
So the idea is, machine gives you the right answer, but now it's going to slow down because you have a person sitting there. And so that's from an industry, you know, if I was in industry, that's what I would say is, this is great. So now tell me how I actually solve the problem of mechanized or automated packing, right? Because that's where the benefit is. Now it's quick, it's fast, and you're going to save me 40, 60% of my packaging costs, which is what, you know, a business would really like. So it's
I think I didn't fully mention, but that is actually what we were talking about as a future goal. So it's the robot that's going to be implementing once you get the maps and stuff. Yeah. So, yeah.
Do you think this can have applications in moving?
Sorry?
Moving industries?
I think so.
Like in large scale businesses moving from one side to the other
It could definitely be applied, I feel. Sorry?
We can, talk about like moving trucks like U-Haul maybe. We can apply these, solutions in U-Haul, stuff like that. Furnitures.
Yeah,
Exactly, furnitures.
Furniture and stuff. So yeah.
How would you say extend your model that say that you have an additional constraint that heavier packages should go on bottom?
Could you repeat the question one more time?
If you have an additional constraint, for example, heavier packages should go on bottom, lighter packages go on top, how would you add that to the model?
So our model, I feel, also includes that, but we weren't able to fully talk in the math behind it. So it first puts all the objects at the bottom, and then it stacks up and tries to minimize the total height covered by all the objects in that box. So yeah, if that answers your question. Oh, by the weight. So that's again like a future goal, I'd say, like how I mentioned about the QR code that would give the direct dimensions, weight, etc. of the shape, which they can directly be applied to our model. So yeah.
I like the fact that you took on this problem, right? Because most engineers don't like.
It's very complex, yeah.
Stuff,
Yeah.
And stuff that doesn't fit into a square box.
Exactly.
It's odd size.
Yeah.
That's a real challenge, and you guys took that on. I commend you for that.
Thank you. Thank you.
Hi everyone, we're group 5 with Motion MS. I'm Brianna.
I'm Dylan.
And I'm Noah.
We first want to give acknowledgement to Dr. Soha Saleh and Michael Glasson, who have been helping us along throughout our project. So what we did is we set out to design a system that standardizes motion capture with markerless technology and also produces metrics to quantify impairment. So we wanted to find that middle ground between accuracy and accessibility. So to develop a product with sufficient accuracy that paired with the value offered in its high affordability and accessibility provided a favorable alternative to traditional marker-based motion capture for impairments. So why is this needed? So key target metrics like these are key indicators for doctors who are evaluating patients with physical impairments like multiple sclerosis. And in order to do this, you need kinematic data, and research teams really need a reliable way to capture this data that doesn't require patients who already have physical restrictions to travel to these gate labs that are also extremely costly and require a lot of technological expertise to operate.
So the problem with most of these traditional motion capture systems is that they're hard to set up, they're expensive, and they're hard to operate. So for our product is a pipeline that uses our standardized method and pushes through our code to develop the key metrics that the doctors need. The first step in our product is setting up the product. You walk the 14 feet path set at specific dimensions from the cameras, as shown in the black circles. From the iOS devices are then captured. The iOS devices capture the. Okay, I guess in this screen you showed. This is the capture screen that shows how to This capture screen shows the metrics that the patients need to enter, and then the iOS devices are then recording what's showed on the right.
All right, so once you've actually captured data within OpenCap, the next thing is to input that data through our custom Python script. So on screen here, you could see essentially what the end user would see when using our Python script. Essentially, they'd enter both the respective session ID they'd wish to analyze, as well as the trial name they'd wish to analyze. And once they've entered those parameters into the code then goes ahead and calculates a number of different metrics. I'll give a brief breakdown right now.
Cadence is calculated, which is essentially steps taken per minute. Stride length is calculated, which is the horizontal displacement within a consecutive heel strike. And step symmetry is also calculated, which is essentially comparing the left step lengths to the right step lengths and then forming a ratio. And finally, this is all visualized using both numeric metrics as well as graphs that the research team can use to make better assessments on a patient's current status. So the first step in developing our product was choosing a markerless motion capture system. The system that we chose was OpenCap, which is an open source platform which works by capturing video through syncing iOS devices. And then once a subject performs some gait cycle or movement, it then creates a coordinate time series, somewhat of a 3D mesh, which is then able to be analyzed. This software is also currently in its beta stage.
So we developed this by varying different metrics. So we varied patients, camera angles, camera distances, locations, and lighting conditions. By this, we standardized the different lengths, different angles, and other metrics that we needed until we got the desired range of motion that we wanted. And we inputted this into OpenCap, and we got the hardware and software requirements, the setup specifications, such as the distances, angles, and we finally created the step-by-step instruction and troubleshooting guide that users need.
And then once again, to just give a brief breakdown of how impairments calculated or quantified, you first take the time series data captured from OpenCap, then you put that through our custom Python script, and then it's visualized in both integer metrics as well as graphical interpretations.
So a large component of our project is proving that our product produces a level of accuracy that when paired with its accessibility, it makes it a alternative to traditional motion capture methods. So to validate this, we went to a gait lab and we conducted 50 trials with 5 different patients or subjects that were simultaneously captured by the marker-based system and our markerless system. And then we processed all the data that we collected, generated the metrics, and we assumed the marker-based metrics as true values. And we use that to calculate the accuracy of our system's metrics. And we determined that it resulted in 92% average accuracy. Due to time constraints, we weren't able to process the marker-based data on the software that's designed for it, that's exclusive to the lab. So we had to use our alternative scripts. So we we believe that if we had used the accompanying software, we would have resulted in a higher accuracy. So the value of our product comes from 4 different areas, one being cost. It's a free software platform, and it uses low cost and readily available equipment. It's also accessible in that this product can be brought to the patient, and from there you can get more consistent and more frequent collection. We also increased usability, so you don't need to have an engineering background to operate this. It's a standardized procedure that any physician or doctor can implement. And then we also brought analysis capabilities to it, in that we can then take the specific data structure that it outputs and process that to generate our target metrics. And all of this comes with 92% accuracy. So in conclusion, what we did is we created a standardized collection procedure. We developed a program to compute the target metrics, and then we put together a start-to-end, step-by-step user guide, and all together with the OpenCap software, we created Motion MS. Thank you.
So you compare marker versus markerless, and I think you said, consider marker to be truth accuracy.
Yeah.
And so 90, but one of the questions for me would be sort of, if X equals X, that's accurate. What was the sort of degree of variance you saw in terms of how far off they were? Because I mean, if this could be, it was measured, the mean variance was centimeters or millimeters, that's great. If it's was the variance you saw?
Yeah, so the variance we saw, so for a metric like stride length, for example, we would see maybe a difference of 0.1 meter or something like that. But what these metrics are ultimately used is they're also plotted in like charts, and from there physicians can more so see trends in the data. So yeah, it's more so they're able to see the trends and get a general idea of how the patients like yeah.
Progressing. I can think of lots of applications where, I mean, this is a great application, but the idea of a easy markerless sort of in space be able to, and if you're reasonably good accuracy, that solves lots of problems. And I can think of, thousands of applications where companies would like to, be able to use a project like this.
Not only that, but if you go the other way, in sports, right, it's about efficiency of motion.
Yeah.
So have you thought about going the other way and measuring the efficiency of an athlete's motion to optimize that?
Yeah, we selected this particular application because we connected with a physician at Rutgers School of Health Professions who was specifically looking for this type of solution. So that's kind of where we started. But when we first approached the idea of different ways to gather kinematic metrics, we definitely recognize that like athletic performance is definitely a big market that this could be applicable to, and like highly profitable, I guess. But
That's where your accuracy and your low cost is going to come in.
Mhm.
Because if you can sell this as a low cost net with high accuracy, you've got the market beat.
Mhm.
So, but yeah, nice job.
Thank you.
Oh, here.
All right, good morning, everyone. So I'm Rosemary.
I'm Natalie. And I'm Jennifer.
And we're Run IQ. First, want to give a special thanks to Axel for providing us with our sensors and Yulin RTA for helping us with the hardware. So we found a problem that people often struggle to recognize when to stop or when they're overtraining. This causes up to 79% of people who run for fitness to sustain extremity overuse injury. So we found a solution, a product that measures fatigue in long-distance runners to minimize injuries. So the question we want to answer is, how can you figure out the right amount of training? So how does Run IQ work? Well, first, from the user's perspective, they'll be placing pressure sensors to your shoe insoles, and once you start running, our system visualizes the pressure information using heat maps. Then, Run IQ will display a real-time fatigue index, and if your fatigue score goes over the safe threshold, Run IQ sends an alert meaning that your feet are getting tired. So the user can take a break or adjust their running technique if needed. So this is our demo. The normal walk shows the recommended heel-to-toe motion, and the fatigue walk shows the change in your feet posture due to the fatigue. And this would trigger our system into giving a warning when you exceed the safe threshold.
All right, now moving on to our system overview. As it was already mentioned, RunIQ collects the data of the user as they're running. Then if there's any abnormal values within the collected data, during this specific activity, our system will send a trigger warning pointing out a fatigue message to the user. Now our system, to go more in depth, our system relies more on the fatigue index model. This is an equation that quantifies how tired your feet are. Some of the inputs for this equation include an individual index values for your right foot and left foot, which are both calculated individually but at the same time. So these numbers are mainly based on the collected pressure data, and each value indicates the pressure distribution and the symmetry of your foot. Now, why are these metrics even important? To begin with, based on the gait cycle, running relies on a heel-to-toe motion. And as you can see on the bottom right, as fatigue begins to set in, it mainly impacts the pressure distribution and symmetry of your foot. So as a result, it mainly negative impacts the pressure shift and overall imbalance of your feet, and it mainly affects the posture of both of your feet as you're running. All right, so for our first metric, pressure distribution, here we'll be focusing on the medial lateral ratio. This is an equation that takes into account 7 specific subregions within each of your foot. As you can see on the top right, on the feet, these subregions are located within the medial side, which is the inner area of your foot, and the lateral side, which is the outer area of your foot. So in this case, some of the thresholds that indicate fatigue lie above and below 0. However, when the ratio output is closer to 0 or even 0, it would indicate no fatigue, as there is an even load distribution across both of your feet.
All right, so let's get into how the coding works for this one. So instead of just putting lines of code, essentially this is the method that we use. First off, we have to load in the data, which is a 8x31 matrix, as we've talked about before. And then we have to split it. I'm not sure if you guys could see it, but we split it manually on Excel on the slide to begin with. And then from those splits, we put that exact region into our code to then automate it. And then once we have those individual regions, we could plot it into the equation you saw on the last slide to get the medial lateral ratio for each instance. But the problem is our sensors actually do output more than 1 sample per second because we want more accuracy. So it's actually not a whole step. It's like part of a step throughout the entire thing. So we want to take the average of a step because then we don't want to analyze it like half a step. That's our step group assignment. And on the right, I guess, on the right, you see that this is the results of one of our trials.
All right, now moving on to our second metric, asymmetry. Here we'll be focusing on the following equation, which takes into account 3 components. The first one being asymmetry total, which is the total pressure of your foot, asymmetry medial lateral pressure, which is in terms of the width of your foot, and asymmetry forefoot heel pressure, which is in terms of the length of your foot. As you can see on the diagram on your right, here we consider individual asymmetry indices for each foot, your right foot and left foot, and then we compare them. These calculations are to make sure that they both stay within the 50 to 50 ideal range during the distribution of pressure as you step.
And going to the coding again. So for this matrix, it's the same steps basically where we load in the data, split the regions, do the calculations based on the equations for before, and same step group where we want to calculate the average over a step and not just individual instances. And on this slide, you just see the splits that we did. It's a lot simpler than the last one. And on the bottom, once again, it's a result for one of our trials. So why are we yapping about like these equations? The main problem here is we're trying to actually find, they combine together to get a fatigue index score. So also on the slide, you see that we combined both the medial lateral equation that we've been talking about and the asymmetry index that we've been talking about too by taking the average of those for one sensor. And then we took the average of that sensor, both sensors at the same time to get the overall score. And going on, since now you guys sort of know how our system works, how are we testing it? Our main testing metric is the heart rate variability. What this is basically a measure of how your body responds to like stress or relaxation. And why we're looking at it is because the lower heart HRV score basically can signify stress, fatigue, or overtraining, which is exactly what we're looking for. And going on to actual testing, if the video could play. You can just tap it. So that's one of our members doing the testing, but I'll walk you through the cycle as the video is playing. So we have 3 main activities: a walk on the treadmill. Gotta speed it up, yeah. So a walk on a treadmill. Yeah. And then the activity she's doing, the runnings, the calf rises to get herself tired, and then another walk to basically have a comparison. And between each, we have a HRV check as well, just to capture any instances of fatigue status changes or anything like that. And onto the, just click again. Okay. So how are we sure that the user is truly fatigued when we get into our second walk? So essentially it's just the HRV. When you look at the chart over there, the main line that you want to focus on is the black line on the bottom. That should be by far the lowest point on all of the trials. And because it's consistently the lowest, I feel like it's justifiable enough where we say that our control groups are mostly fatigued on the second trial, and then on the first trial they are not fatigued, so we could use those data safely. And once we actually can use those data safely, now we can justify or compare our results, our model results to actual control group results. And for us, it's only 8 out of the 12 times that's actually accurate.
Okay, so I'm gonna go really quickly. So why should you choose RunIQ? Well, as you can see, RunIQ displays the fatigue more on the go, while the current market displays the fatigue score to see if you're fit to run. So basically, RunIQ is proactive, not reactive. And why should runners care about RunIQ? Well, it prevents injury, optimizes training, and supports long-term health. Thank you.
So currently we actually are doing it individually by person because our matrix are different for like heart, like HRVs and all that. We're pretty different in terms of like body build and just like heart, I guess, beats. So we are currently just mainly focusing on like one member's data right now, so to get a better like measurement for our actual model.
But not everybody's feet are the same, right? Obviously everybody's got different shaped feet. Some people, especially as you get older,
Yes.
shape changes.
That was a big struggle.
That's why I think this, I mean, personally, I think this has real market value if you look at it from an individual perspective. Someone comes in, they create their own baseline, and that becomes a much more accurate indication of when they become fatigued because their feet are different than everybody else, right?
Yes, yes, yes.
Good product.
Oh.
So if you were, again, now I'm the CEO of Nike, right?
That's great.
But you know, leaving even the fatigue aside, so you know, a variable here would be shoe design and how that sort of plays out in terms of you know the impact of more biomechanical friendly shoe designs, which sort of could impact leaving the fatigue side out more. Just now you're collecting the actual data. You know, a shoe that sort of stops pronation, or you know, you could actually you know visually demonstrate. You know, this product should improve an athlete's performance, right? It sort of will improve strike and balance and gait. So I mean, I think you know that's a potential user of a product like this to say, if I'm an athletic design shoe, or even you know, not even athletic shoes, regular shoes, right? I mean, it would really show this is a better shoe for you to wear. Well, good, nice job.
Oh. Okay. I didn't touch anything. I swear.
All right.
This on? How's everyone doing today? Good, good? Yeah. There we go. That's what I like to hear. A little bit of energy in here. Yeah? Okay, okay.
All right, they're the last and most energetic, so head on there.
We'll try. We'll try. Good morning, everyone. My name is Doug.
I'm Will. And I'm Anthony.
And we are on time systems. Let's get into it. So in manufacturing, time studies they provide very valuable insights into processes, and they're currently a hassle. Traditional methods are time-consuming, labor-intensive, and often miss crucial metrics that could drastically improve efficiency. And so that's where we come into play with our solution of a unified time study and ergonomics tracking system that allows engineers at manufacturing companies to make more informed decisions for both their processes and their people. And so while working on this, we used our technology to test our hypothesis of whether or not posture affects productivity. And so this is our product, 3 main components. We'll dive a little bit deeper into it later. We have a live posture tracking system, an automated time study system, and then those funnel into a dashboard. And so this is a system demonstration up on the screen here, all 3 elements of our project in action. And I know it might seem a little bit overwhelming and complex, and that's the point. We have all 3 elements of our product continuously working together to ensure that our customers can collect the data that they need. And so let's talk about the methodology here. For the posture tracking system, one of our fellow classmates was kind enough to participate in one of our tests. You could see a skeleton sketch here in the green tracking the ear, shoulder, and hip. And so a score is calculated based on those angles, and it's displayed on the top left here. And the great thing about this is that you could get real-time feedback on your posture. And so breaking down the technology a little bit more, the input is a live video feed, and then using one of our main Python packages, MediaPipe, which is based on machine learning, we locate the key landmarks on the body, and then a posture is then scored using the angles on the body along with a comprehensive scoring system that we formulated. And then that posture score is displayed live. And then the outputs, you have a recording with the skeleton sketch, as you saw on the last slide, along with the chart of the posture score over time.
Now on to our no device technology. This part is defined by these three important aspects that are sure to blow your socks off. First is our custom hardware. We took this approach so we can control how our users interact and set up these devices. We sampled multiple microcontrollers to find out which feature set works best for our application and decided to go with the ESP32 dev board for its vast amounts of I/O as well as wireless capabilities. Next is our 3D printed enclosure. This gives our product a better fit and finish and feels good in the hands. It also protects the sensitive electronics inside. And finally, the software, and there's a lot of it. We created custom pipelines to send, receive, manage, and even display our data in the way we want. A custom interface was also written for the no devices, allowing our customers to set up the line and station IDs with ease. We put in all this effort to make it as easy as possible so it can be utilized by as many companies. And now onto our unified system overview. We have the data from the cameras as well as our no devices fed into the laptop. All this data is stored into SQLite to easily access it using Python and JavaScript. And now onto industry testing. We worked with a local company called HumanScale. They're a high-end office furniture manufacturing company, and currently their lines don't have a lot of live analytics, which is good for us because we can fill that void. We worked with the engineers to run multiple trials using anywhere from 1 to 7 of our devices, and we were able to provide meaningful data on their line's performance while the engineers were doing something else, like attending meetings, working on drawings, or maybe scrolling through Facebook Marketplace. We also did, we tested our hypothesis here in the Industrial Systems Engineering Lab. We utilized our hardware, collecting time study data as well as ergonomic data simultaneously, and then performed analysis on it later to determine if our hypothesis is true. And on to Anthony.
So now moving on to how we interpreted the results of what we got. So first, our hypothesis testing that we completed. The first thing that we did is we mapped the posture score to the exact time studies. As you can see, the top one is the posture score, the bottom line is your time study with the bumps indicating that a button was pressed, indicating that a cycle was completed. With the cycle runs that we completed, our initial results showed that there was little to no direct effect of posture on productivity. In order to validate this, we used the Mann-Whitney U test to see if there was a difference between the data set, although we're not making a definitive conclusion because we did only have a limited data set of about 100 data points and only did one work process. So we are suggesting testing this on several different work processes and gathering more data points before coming to a definitive conclusion. Next, for our system results, the bread and butter of what we're offering our customers is our metrics dashboard. So the two key parts that I want to highlight are our live posture analysis and our station times. That live posture analysis graph that you see up there was obtained in real time. Someone is moving and changing their posture, and we're able to make that graph in real time. We'd be able to show you that later. And also our average station times, we're able to show efficiency and cycle time in real time, and that updates. So we can get you that information as soon as you need it. No need for playback at a later time. We also validated our system using several different methods. And the thing that I want to really highlight about our project is we were very proud of the results that we were able to achieve, but we're equally as proud of the way that we were able to do it. Coming into this project, we wanted to make something that is accessible to many different companies and gives them the information that they need while coming in at a low price point. So what we did was we adapted a system that has wireless capabilities, plug and play, it's infinitely scalable, and it's a low-cost solution. So we built something that you could plug in and have set up in about a half hour, and you will need no technical assistance, essentially, and you could have it up and running and getting that information you need as soon as possible. So finally, going into our value proposition and impact, we took a three-legged stool approach with our value proposition. Just as a stool needs all three of its legs to stand, our product needs three of these components in order to be successful. So first with our customer, our engineers, by providing them with real-time time study metrics, they are able to spend their time on more value-added activities rather than sitting there with a clipboard and writing down times. They could do more analysis. Next, for our employees, with the ergonomic tracking system, we're providing them with key health metrics that could allow them to make changes to their posture and the way they're working before dire health effects may set in long term. And finally, for our business metrics, by implementing these time studies and making work processes efficient at a quicker rate, we can get products out the door faster to customers, and it also opens the door to additional profit opportunities because engineers could spend their time on more value-added activities going forward. So in conclusion, our goal with this project is to maximize performance and minimize strain. Thank you, and we're happy to take any questions you guys have.
You're the CEO of a manufacturing company.
You guys did a really good job. I like how you took a traditional industrial engineering procedure and modernized it. So congratulations on that.
Thank you.
So just real quickly, take me through what is the customer. So your customer is the engineer, also the employee, and the dashboard. Is the dashboard giving that real time data back to the people on the line, or is that more of a management tool? And then how does the data get into the real time to the people who can make the changes on the line to improve?
So the node devices, they communicate wirelessly, saving the data into SQLite, and the dashboard can be opened up. SQLite is a database framework that we're utilizing to just save all this data because there's quite a lot of, every time the device is pinged, it writes a new line. So it just allows us to easily read and write to it. But the dashboard can be opened up on any computer, whether it be line side next to a technician or in front of the, let's say, the manufacturing manager. So
it's meant to be more of a management tool.
Yes.
Okay, real-time feedback tool. Is there real-time feedback to the people who are on the line who use that data?
Yeah, so the idea is if we were to roll this out as a product, you would have the management side, which is more of what we were showing you today, but the live posture score could also be fed to the actual employee because the goal is at the end of the day, you want to help them improve their posture. So they wouldn't see the whole comprehensive dashboard essentially that they're seeing because it's details that they don't necessarily need, but we would have a specific part of the dashboard that shows just the posture score for that employee.
One last thing. So traditionally, and again, I'm older than dirt, and dinosaurs ruled when I was here, but time studies were viewed horribly by employees, right? It's intrusive. I'm curious. So you actually rolled this out, which is unbelievable. You went out to a manufacturer. What was the feedback from the actual employees?
So our original method to ping the device was using a small PCB that had a sensor on it, and we would place it on the manufacturing line. So when a product slides by, it would ping automatically. The operator didn't have to do anything. We realized most manufacturing lines are set up where it's a flat surface that they will work on and place the object anywhere. So we could not reliably ping it using that method. So we ended up going with more of a button that they would tap, and then they were fine using that because it's non-intrusive and it just sits by the side. But the biggest issue is they need to hit it consistently. There were issues where one operator would hit it 100% of the time and others would forget about it. But that comes down to training and educating the employees on how to work properly.
And when you talk to the employees or managers to talk to you, how is this sort of couched? This is a tool to help me, Jerry McGuire, help me help you, right? You'll improve your posture, you'll feel better, we'll get higher productivity, win-win-win. I'd be curious sort of how the management of the company talk to the employees about implementing this test.
Yeah, so it's very interesting. I feel it's very important with a product. You have to pitch it to whoever your customer is going to be in that state. And it was a different situation of going up to the employees and letting them know that this is going to be something that's going to make your life more efficient and make your life healthier. Meanwhile, you go to the management side, kind of circling back to what you said to an earlier group later. Employees are your most expensive asset. So now telling these companies the angle of you're going to save them all this time and they're going to be able to use those employees to do more value-added things and help their company, that's how you frame it to them. And then you bring it to the employees with more of the ergonomic side of the project.
All right. right, thank you everybody. So this concludes the first half of our presentation. And I welcome you to go outside, grab a coffee, grab some sweets. We'll come back in 10:20.
Temperature curve looks like for coffee while it's in the roaster. You start off at the charge temperature. This is the initial temperature of the roaster before the beans are dropped. And then you hit what's called the turning point, where the temperature in the beans and the roaster hits an equilibrium. You then hit the yellow phase and the brown phase, which this is where the moisture content in the coffee is going down, until you hit an event called first crack. First crack is a bigger bean because it's very important. First crack is when the moisture and the pressure in the bean hits a certain point where it actually bursts open, like you expect like a popcorn kernel would. This is important because after this point, a lot of the development time happens after first crack because it's lost all its moisture, so it heats up very rapidly. And this is important in, next slide, defects in consistency. So you can see in the graph, we have in blue, we have what a normal curve is, and then we have an example of a scorched curve and an underdeveloped curve. We can see this is what scorched coffee looks like. You can see there's like black beans in there, which we don't want, and then underdeveloped coffee is in that like nice brown color. This is because scorched coffee, you can see, started at too high of a temperature, and then it increased too rapidly, so it hit the target end temperature when you drop the beans out of the roaster too quickly, and then the opposite for underdeveloped coffee where it took too long.
So here we have a working example of our system. Essentially, on the right side, we have the actual motor controller controlling the gas valve, which controls the heat, essentially. And then on the left side, we have the graph, which tells us like what the predicted and actual temperatures are happening, and then how they're all converging onto the target. Next slide. So this is our system. We have a Cormorant CR600 roaster and a couple of temperature sensors in the roaster. We also have our stepper motor and gas valve set up on the side, and the computer to control everything. Next slide. So the most important part about our system is that the inputs and outputs are happening continuously every second, and they make the changes in real time. So our inputs are the temperature data from the temperature sensors, and our target profile, which the user will give the model, so it trains on it. And then the model is an ML model we developed. And then after that, the model will spit out temperature and predictions, temperature and stepper motor positions predictions, to essentially make it predict the temperature and control it over time. Next slide. And based off of that, we did some tests. We did a roast for a target roast essentially, and that was our control group. And then after that, we did a roast, the same roast. We tried to replicate the same roast with our system, and then we tried to replicate it manually, and then with the PID controller. We did a mean squared error analysis on it, and we found that ours was the lowest, as you can see over there. Next slide. We also did a qualitative test, and we did color sensing using a spectrometer. And as you can see, the target was about a medium roast, and then coffee break did a little medium dark, manual roast, replication was a medium light, and the PID was a very light, which was really off. Next slide.
All right, so what value does this bring to the customers, the small roasters that are our target audience? The first one is that our controller will allow roasters the opportunity to replicate their roasts with better precision and accuracy than current existing automated methods. We do this through a predictive model that will determine the bean temperature's trajectory, as opposed to existing automated softwares that are only reactive. This can cause more defects, and our system will see the defects before and correct them. And lastly, it has easy integration. Most of the components of our system are sensors and technology that coffee roasters would already have, allowing for easy plug and play. And so just to add more to the contributions of a typical coffee roaster setup, we are adding our machine learning predictions, which will predict the actuation of a gas valve in order to replicate the curve more accurately. And again, the big emphasis of this is the real-time adjustments to avoid any potential defects. It will adjust in real time to compensate for any variations between batches. Thank you. CEO of Starbucks.
I was going to say, how is Starbucks doing this today, and who is your target market, and how much does something like this cost versus what it's going to add to their
So where our target is smaller coffee roasters who are more interested in single origin coffee. This is because a company like a Folgers or a Starbucks is interested more in consistency. And the way to get more consistent coffee easier is just to roast everything rather dark. So as you basically roast out anything that's interesting about the coffee and just make it flatline. This is important for them because they're sourcing their coffee from all over the world, like Brazil and Colombia and whatnot, and they need it to all taste the same. But what single origin coffee is, they actually want you, their marketing is for, this is a Brazilian coffee, this is a Colombian coffee. So like they don't want to roast it very dark, they want to actually have those flavor notes in it. That's why a controller that Starbucks and whatnot use is going to be more robust, like rudimentary controller, like a PID or whatnot, because they're just going to roast it very darkly and they don't really care. But a lot of the very good consistencies and defects that you get when you do lighter roasters are a lot more hard to control that way, which is where our card comes in.
So,
CEO of Starbucks.
No, now I'm a boutique owner of a coffee roaster.
Okay.
I am.
Love Halloween.
I love Halloween. You're never alone with schizophrenia. One of the things I sort of note is if you were to go out and talk to people who run these, how much of sort of what they do is art versus science, right? Because you guys are turning this as, I'm going to predict, I'm going to do this, at this amount of time, this amount of temperature, this is what my result is going to be. And I guess I'm curious, have you talked to roasters and said, like, how much of this is really art?
So one of our members that we collaborated with was Daniel's father, who's an actual coffee roaster. So yes, yeah, we did consult with industry professionals, and the thing we found was that the most important part of our project is the roaster will give the model the curve that they want to replicate. So in the sense of what we're replicating, it is art. It is like a thing that roasters get from experience. And we're not trying to take that away. Essentially, the roaster makes a roast, and they like that roast. They want to replicate it. They just give that to the machine, and then it feeds it to the ML model, and then it replicates that. So that's the goal.
And so when you have the desired roast pattern, right? So you know that. So I guess one of the questions for the roast would be is, so how much variability occurs because this is an organic product, right? The beans don't always grow up in the same. So moisture content, things of that. How do you take that into account?
That's why we have real-time adjustments, because you can train a model, but you can train your model using a data set that you had for 1 year, but then say the next crop rotation of beans could be entirely different. That's why we have real-time adjustments, so that it is not only are we feeding in new data sets into the model as it goes along, but we're also doing real-time adjustments to take into consider those variabilities. So we're taking in actual sensor data as far as prehistorical data. Those are the two main temperature or sensors, yes.
But there are other variables that impact?
There are other variables as well, like size of coffee, lot of size of coffee, that you would train into the model to do this as well. Yes.
Thank you.
All right. That's the one, right? Double check. Double check. That's the one. Yes. All right, you guys are doing great. That's great.
Hi everyone, so this is our project, Emotoplay. And this is our team, so my name's Ruchi.
I'm Ariani.
I'm Nick.
So moving on to the problem statement. Currently there are 11.1 million video game developers worldwide, with the job demand only increasing. The majority of the video game industry uses methods including observations, interviews, and surveys to get user emotional feedback on the products that they launch. So why does this matter? Well, ultimately, this introduces personal and survey design biases, recall errors, and lacks the ability to track emotions at every second of gameplay. Therefore, we present Emotoplay. This seeks to help video game companies gain visibility on more accurate emotional analysis. So what exactly is Emotoplay? Emotoplay integrates EEG brainwave data and facial action units to monitor emotions in users while gaming. This data is feature engineered and inputted into a trained machine learning model, which analyzes 6 different emotions, including neutral, happy, sad, fear, anger, and surprise. The model then outputs the dominant emotion at each timestamp during gameplay, and these results are summarized in an emotion analysis dashboard. So this slide shows you a glimpse of the dashboard that I mentioned in the previous slide. So as you can see, video game companies can not only see individual users' emotional responses, but also get an overall analysis of all of the users that they tested. So with this innovation, our group hypothesizes that by combining EEG sensors and facial recognition technologies, we aim to detect emotions in users more accurately than relying on a single technology, but more specifically in the video game setting.
This next slide will show a demonstration of our system in action when a participant felt scared while watching a video. As you can see to the dashboard to the right, the dominant emotion switches from neutral to fear when the participant looks scared. So how do we get to that result? We need to collect both EEG data and also facial recognition data, so we use the Emotive Insight EEG headset, which has 5 channels corresponding to the different brainwaves. We also incorporated a webcam with our computer system so that we could record facial expressions of each participant during our tests. Here's some of the software we use to process our data and ultimately create our machine learning model. So the first step in our overall methodology was creating a testing environment and collecting valuable data for our model. To do this, we tested 10 participants by having them watch a compilation of 5 clinically researched videos that are meant to induce a specific emotion. In between each of these videos, we also placed a calming video so that the participant got the chance to return to a neutral state. So as you can see to the image to the right, while the participant watched the video, they had the headset capturing the brain waves as well as the webcam recording their face while they watched the 7-minute-long video. After this process, we needed to process each of the video recordings from the webcam using OpenFace so that we could add the facial bounding box and the facial action units that you saw on the demo. And then after we collected all of our data, we needed to process it. So the first step here was labeling the timestamps with the emotions that we intended the participants to face at each of those times. We also filter the data so that we could remove any noise from the EEG data and any inaccuracies in the facial action unit data, say if someone else walked into the frame. And then to make our model as robust as possible, we wanted to conduct some feature engineering. So first, we computed several statistical metrics on both of our data sets on a rolling window so that the model could learn from any temporal patterns. We also looked specifically at each channel and grouped together brainwaves that typically align with a specific emotion or a cognitive state and calculated the band power ratio between them. Using these new inputs, we inputted that into our machine learning model. We tested several and came up with choosing the XGBoost classification model since we got the best results after performing some hyperparameter tuning and catering it towards our goal of emotion classification.
So how could we be sure that our model is accurate? Well, we did the canonical 80-20 test split where we took our big data set and split it into 80% of training data and 20% of testing data. We then ran it through the model and used several performance metrics to be able to analyze how our model performed. And you can see that our accuracy score of almost 94%, which is pretty decent. And then in the graph there, you'll see some of the other performance metrics that are more insightful into the specific classifications. So they give an idea of kind of the localized accuracy for each emotion. And you'll see that fear and surprise are a little bit lower than the others, and that's primarily because they're such short-lived emotions, so it can be difficult to get a larger training set, and we believe that with more data collection, we would be able to produce further accuracies in those emotions as well. So then we wanted to go back to our original hypothesis where we thought that combining the technologies would prove beneficial. And here you'll see those 4 metrics that I talked about previously in comparing to the 3 technologies. First, just the EEG, then the facial expression, and then finally our product. And you'll notice there is a slight improvement in performance metrics with our technology, though not super significantly different. And the conclusions we draw from this are kind of twofold. First, it shows promise that if we were able to do further data analysis and processing, particularly on the EEG side, it's a very complicated sensor and it was new to us. So if we did more, if we had a greater knowledge about that, we believe that we could widen this gap and make our technology even more beneficial than single technologies that are already out there. And secondly, there's other benefits of the EEG sensor that we haven't explored. So this makes this product even expandable by having the 2 technologies together. For instance, emotional states like stress or attentiveness. And then here's the big one. Why is our product valuable? Well, first, it provides a second-by-second emotional analysis into what's happening during a gameplay, for instance. Unlike surveys, which are just kind of paint a broad brush over the entire time span, this technology gives you second-by-second analysis. Secondly, there's a multimodal data stream, right? We have two different sources of data, which is beneficial kind of in two ways. First, if one of the sensor malfunctions or your specific environment that you're testing on isn't suitable to a particular sensor, maybe it's dark, maybe the sensor is kind of loose, our model has shown success in all different kinds of environments. And then finally, it provides a bias-free emotional analysis. Going back to the surveys, they can be hindered by various, cultural backgrounds or whatever, and this provides, we trained our model with a diverse training set that allows us to hopefully ensure impartial classification. And then finally, just some broader contributions that we made. We mentioned our testing environment that was unique, that hopefully makes our model better performing than others. The kind of synchronization of the dual streams together took a lot of work, and we're pretty proud of that. And then we built a custom novel machine learning model and implementation framework that allows you to see the results in a timely manner. Thank you, everyone.
how they might use something like this, right? Because in many ways, you're monitoring what's happening during the game, but the designer is the one who's actually trying to elicit a response, right? Because they've created it to scare you or make you happy or things like that. So I'm just sort of curious, would there be interest in this from like a developer's perspective, saying, I'm trying to get response X, and in fact, if I didn't get X, I got Y, and do I adjust? Or so is that how, I mean, what would be the commercial use, or how something like this would be used?
Well, yeah, to address like the first part of your question, I think we didn't get a chance to talk to a video game developer just yet because we wanted to make sure that we had a valuable data set that was tested by a video, that we knew where the emotions were placed, because different people react differently. So that was the first step, just creating that valuable data set. And then now it's kind of like a plug and play for video game developers. But also I think, yeah, it's very valuable for a video game developer to see, because another big avenue in video gaming in the industry currently is like dynamic adjustment to players' decisions while playing games. So this could eventually lead to maybe changing the video game setting per player by their emotion, if in a much future sense.
You're right. It wouldn't necessarily like provide a recommendation for what to do, certainly in this framework. But I think kind of that's where the artistic kind of liberty comes from the game designer himself, and he can kind of think about, okay, this didn't work. Maybe look past on previous results or something like that.
And I love your idea about, I mean, if the trend really is dynamic modification, right? This is how they actually get the input to say, scare this person now, or don't. So that's.
Oh, you are not enough scared. Let's
Yeah. And we saw something similar last year, but it didn't have the brainwave component to it. So, you guys did a lot of good due diligence on the whole process and how you went through it. But I agree with John, there should have been a little bit more in the value proposition to talk about why this is important to video game developers and companies in general. Some of it, I think you guys think it's pretty well known kind of why this is important. But for some folks that, like me, that don't play a lot of video games, you might want to just kind of make sure you don't gloss that.
So this may be important on quality assurance stage, meaning that the software, okay, was made and let's test it.
Yeah.
We plan this scene to scare, or we plan this scene to like person to love.
Right. Yeah.
Did we achieve it or not?
Yeah. Yeah. Good. That makes sense.
So does your model output like fear or like 50% fear and 50% surprise?
So it's a deterministic model. It'll predict the most likely emotion. No, it's just a straight output. It doesn't give a probability distribution. Yeah.
You're sad.
Yes. Yes. It's deterministic. Yep.
And was there any, I mean, I guess, I don't know, maybe fear, and I don't know, of the 6 you had laid out, sad or angry, or how clear was the differentiation between the emotions?
Yeah, we tried in our videos. It comes from a kind of a clinical data set where participants ranked how much they responded to a particular emotion by each video, and we tried to pick videos that were explicitly succinct. But a broader application of our model could be: did your game produce any emotion at all? And so there's kind of a distinction for baseline there. Thank you.
Slides, right?
Yes. Yeah, only want to use slides.
No, two of one.
Oh.
Yes. More money than God.
All right.
What do you think? This is represent your life. We're going to who's gonna answer. Oh, do you want to use this one? No.
Hello. Okay, good morning everyone. We are group 14 and this is our project on an interface you conduct.
A special thanks to Dr. Julia Baumanis. She is the Mason Gross's conducting professor as well as the Rutgers band director, and she is our mentor for our project.
I'm Dina.
I'm Alexis.
And I'm Emmeline.
And this is our team. So the problem at hand is that music students currently face challenges when practicing conducting outside of the classroom. Sorry about that. Our goal was to develop a learning tool that will provide orchestra conducting exercises and feedback to improve students' techniques, in our case specifically for the Mason Gross School of Arts.
So the value proposition for this project can be divided in three categories. First being cultural impact. You Conduct aims to support the growth of future conductors in the music community by providing an additional resource to be used for practice. Our educational and social value is that it allows for conducting education to be practiced in various environments. Conversely, our economic values lie in our strive to promote an inexpensive learning tool that does not solely rely on classes for students to learn.
So the system structure for this presentation, just for simplicity, we first want to go through the right hand for the conductor, which focuses on tempo meter, ergonomics, and pitch correction, and then lastly we'll be going over the left hand Le Bon movements. So first right hand.
On the left side of this PowerPoint is our demonstration of the right hand model. In this video, I initialized a 4/4 time signature and practiced 4/4 as well, and received an overall confidence interval of 50%. In the right video, I tried to keep the same 4/4 time signature input. However, I intentionally practiced a different gesture, which in this case is 3/4. The model was able to recognize that the gesture that I was practicing was 3/4 instead of the 4/4 gesture, and it gave me a confidence score of 38%. The scores are slightly close in accuracy due to the fact that these gestures are very similar in their movements. As you can see on the left and the right side, this is how the gesture is performed. As well as the fact that our database will need additional values for our data collection. Just to go over some terminology, we'll be focusing on type signature, beat pattern, and two different styles. One legato, meaning the smooth and connected way of performing these motions, and staccato, meaning the space between the gesture that you're conducting. Key components for our model recognition lie on the tracking availability of our baton tip, these three aspects, the pattern, style, and metronome. In total, we have 18 combinations that we're inputting into our database. The right hand is a depiction of the tool that we're using in order to collect the data.
So ergonomics and pitch correction. We found a survey that said that 64 to 76% of musicians were experiencing repetitive strain injury. For conductors, this was because of incorrect ergonomic technique. This is why we thought it was essential to account for ergonomic mobility in our project. In this next video, you're going to see what occurs when you cross those boundaries that we set, as well as audio feedback that we included to mimic the sound of a theremin to inform practicing students what feedback they're getting back from the orchestra. I ask you to pay close attention to the change in pitch as I move the baton higher and lower. So on the left is an image of us testing that good distance check that you saw at the beginning of that video. And this is done through checking the number of pixels that are on your hand, accounting for a 10% tolerance rate for different individuals. As for the boundaries, obviously not everybody's gonna have those same ergonomic boundaries. Everybody's body is different. So the upper boundary is an approximation of the top of your head through a key point of your nose. And the lower one is a boundary that initializes 2 points below the first tip or the first point of the baton.
So moving on to the left hand, in the first video, you can see the Laban gesture press is being performed by one of Dr. V's students, Simon. The overall feedback is just detecting the overall gesture being detected and also aligning it with the gesture that is initially put in by the user. The accuracy reading is 61%, and this may be due to the fact that Simon is a practicing student. On the second video, a practice gesture is also being processed. However, we're purposely doing the Laban gesture punch intentionally. As you can see, the gesture detected is punch and the accuracy reading is 0. And this is because the punch gesture is significantly different compared to the press gesture. The difference between the left and right hands is that the left hand does not give constant feedback, but actually gives an overall accuracy score. And this change was due to a result of Dr. B's recommendation for this database. So in this diagram, you can see the 8 Laban gestures that are loaded into the database, and also we included the metronome beeps per minute from 60 to 120. In total, we have 24 total combinations. Now, moving on to the methodology. So first, we used a pre-trained model and an LAT light detection to first track our hand landmarks for our left and right hand to separate them into CSV files. Then we utilized a machine learning model to train and standardize our data. Next, we set depth parameters so the users are at a proper distance away from the computer before they initialize the practice session. Then we proceeded to observe the accuracy by using Dr. B's real-time gestures into the user interface to test the accuracy. Finally, the interface varies for each hand. So for example, the left hand focuses just on Laban and the right hand focuses on beat for time signatures and BPM.
So one of the biggest challenges we faced in this project was finding a way to detect the tip of the baton. We went through various different trials in order to do so, first starting with red color tracking, as well as media pipe landmark tracking to try to estimate where we thought the baton tip would be. This, however, was unsuccessful. We then moved on to the Aruco marker tracking, and this was what we implemented for a big portion of our project, but inevitably we realized that it just simply wasn't consistent enough for us to use in our final product. But we did use the green LED light tracking given 2 phases. So in phase 1, we simply used a battery-powered LED, and we attached it to the tip of the baton. But this was very heavy, and this put off the balance of the baton, which is really important for conductors when they're going to be practicing this very often. In phase 2, we made a couple modifications to that light and made it lighter.
Based on Dr. B's reliable movements, the accuracy score for the left hand is about 72%. For the right hand, we were not able to track her movements in the user interface, but we hypothesized that it has an accuracy about 52% due to complexity.
So what is different? Our product is different in complex pattern recognition and ergonomic guidance. This product is intended to be used by Mason Gross's School of the Arts here at Rutgers. So we curated the database with Dr. B's motions. This is how she will be teaching every student of Mason Gross. Our role is to give real-time feedback to those students with flexible design enabled for them to practice in various settings.
Thank you.
I've
Thank you.
never seen this tackled before. So I've played under different
question is, it looks like this is about ergonomics and it's about safety and the health of the conductor, but are you also trying to promote a style that is consistent so that if I'm playing in an orchestra and then move to a different orchestra, those two conductors would have sort of a similar style and I wouldn't have to learn a whole new style all from the beginning?
So yeah, that's a great question. A portion of this project was tackling how we would adjust for the difference in how conductors play. For that reason, we focused on working with Julia. Again, all of our values for our database are from her. We also had her validate the interface. So in regards to different styles again, I'm not sure if you guys remembered, legato and staccato, for instance. The difference in legato is smooth gestures, whereas staccato is like straight to the point, like between the points. These are going to be measured similarly to the first video, where there's a database specifically in legato for each pattern at each BPM. So we have 3/4, 4/4, 2/4 at 60 BPM, 100 BPM, 120. So we have a database specifically for that. In order to compare whether or not the student is performing in legato, it's going to use the same kind of comparison in the database and the interface. Yeah.
Yeah, I also just want to add that one of the big selling points of this is that the main thing is that we are simply providing context to gestures that are already pre-existing. So even though we curated this database based on Dr. B's movements, this can be applied to many different applications, and any conductor can simply use their own data to teach their students.
Exactly. That's really where I see this going.
I think you are missing like large database, which is
Yeah, definitely.
famous conductors, like conducting orchestra. You probably should try interpret their just movements.
Yeah, for the future direction of this project, Dr. B, she's really looking to take this a step further, obviously hopefully with the help of our guidance. We're looking to patent it and test this out, not only with her students, a larger I guess trial and validation with her students, but we're looking to patent it and hopefully get conductors, not only from the department, but from other schools to try it as well in order to help validate and ensure the accuracy. Yes.
Not only from the conductor side of the coin, but also from the orchestra, from the players, right?
Yes.
I mean, really, you've got something here that can, has anything like this been even attempted? Is there anything out there on the market?
So yes, we did our research. Actually, Dr. Baumanis, a long time ago, her dissertation was on creating a training tool that works similarly to this. Unfortunately, she was unable to proceed with that dissertation, but we kind of took off from that, where through our means of method, we wanted to create a training tool that was catered for that. So we did our market research. What was out there? What did she research during her dissertation that could probably compete with our product? So what we came to notice was, yes, there are apps that are intended to help conducting. More specifically, you can see that they're either to keep real-time control or follow beat patterns in music, but we're really emphasizing on the difference between the left-hand conducting and the right-hand conducting. They're completely different. They work together to help create a sound, but we are specifically looking for a kind of that tracking of accuracy, like how close can we get it to it. Mm-hmm.
We discovered that.
Yeah. As we kept going on with this project, we realized there's just so much complexity and layers to it that it makes you really appreciate it, and also just appreciate putting the work into it to help this department.
The major conductors that have been throughout history have something that others don't, and this could help bring that out. So congratulations on a great project.
Thank you.
double check.
That's the one. Yes, it works.
Good morning, everyone. We are Group 6, and we are Shore Sweep. We'd like to say thank you to all of the people that has helped us on this journey throughout our project. So, our problem statement. We defined our problem as ineffective trash cleanup, specifically on beaches. It's time-consuming, physically demanding, and there are many environmental hazards for the people picking up the trash. So, for us, our question is that we're trying to solve is how can we limit human interactions and human factors in cleaning garbage off of our Jersey shores. So how will Shore Sweep work? So there is garbage on the beach. We will fly the drone into the area where the garbage is. It will scan and detect for the garbage, and route will be optimized for the dog to go and pick up the trash from the garbage. So our solution is using the dog and the drone in tandem to limit and reduce human intervention for picking up trash. So the inputs that will be gathered will be the drone. So it will take images from the air, and then those images will be processed, and the route, the path that the dog will take will be optimized, and then the output will be the trash collected. So this is our methodology, our iterative process. So we initially started with an inaccurate model, and we refined it and retrained it to have 99% precision and 96% recall on our object detection model, as well as adjusted the camera settings on the drone to ensure we were mitigating false positives. Through image processing, we created flying constraints for the drone, so we weren't flying it too high that it didn't see the garbage on the beaches or on the testing area, as well as we weren't flying it low enough that it was hitting any obstacles. And we also used the sliding image algorithm, so during detection, the code would look at the large image, and it would break it down and take smaller parts of that large image and scan through that small part of the image to essentially get a more accurate detection of garbage.
All right, so now onto the physical mechanism. As you can see, we designed essentially what it looks like a sand rake over here. This is what's attached to the dog. At first, we came up with an infeasible prototype. It was essentially a soccer net on the back of the dog. However, that ended up having low maneuverability. So with this, we created essentially a swivel joint mechanism that has 3 degrees of freedom, so that it has lateral movement. And onto the trajectory commands, we noticed that Spot lacked proprietary navigation services. So we tried third-party GPS. However, that didn't really work out too well because of accuracy. Therefore, we used trajectory commands that are already built into Spot and dead reckoning alongside of it in order to ensure that Spot was able to traverse through the terrain. So onto our hardware integration. It consists of 4 pillars: the drone, the computer, the Spot dog, and the sweeper. For the drone, as was foretold, it scans the beach. The computer processing all of our data, coming up with a route that we want to send Spot in. Spot's going to traverse the terrain, get to all those locations, and the sweeper's going to pick all that trash up. In terms of our software integration, as aforementioned again, we're using the smaller sliding window approach. This is then translated into or used in the YOLO V8 convolutional neural network model, which is analyzing the trash and detecting it. We're then geolocating all the trash using the GPS metadata on those photos that were taken alongside ground surface distance data in order to find the exact pinpoint locations of the cans. After that, we're grouping all duplicate detections, given that we're taking multiple pictures in different orientations of the trash so that we're able to better accurately pinpoint the trash. And then the route is calculated using the traveling salesman optimization problem. This is just one of the shortest path algorithms that we used. After this, a route is converted, and then it's eventually converted into trajectory commands for the Spot dog to travel. In terms of our processing methodology, we took numerous photos through our flight path. As aforementioned, it's going to be clustered, going to be found in longitude and latitude coordinates with certain confidence levels, and then a shortest path will be developed in addition to the movement commands associated with that shortest path.
Yeah, and so here are 6 key contributions that we have that really emphasizes why short sweep is improving on current tech. As we mentioned, we're using the sliding window approach. We're improving existing Boston Dynamics programs. We're making them a lot more user-friendly. We're also using a custom designed physical mechanism. We have a self-trained CNN model with YOLO V8 as our backbone, our optimized route calculations, and finally, those user-friendly maps that you just saw to recognize trends within the trash. And here you can see our results. On the left, Spot is successfully picking up 1 can of trash with the mechanism on its back. And on the right was the full test, where we took the photos with the drone, we got the coordinates, sent them, created the automated path, and then sent that to Spot, and it's autonomously following those directions. You'll notice that the mechanism isn't on the back of Spot because in our final test, the joint broke twice. We'll cover this a little bit later, but it's we can reasonably assume that because Spot is successfully walking over the cans and was able to do it once, that with the mechanism attached, it would successfully work. And as we said, we're testing on a small stand site. We benchmarked short sweep against a manual trash removal, and we concluded that yes, we were able to reduce significantly the human intervention or the human factor in scanning the beach, identifying objects, grouping the trash, optimizing the path, which a human can't really do, and then actually following that path and collecting the trash. As mentioned, there are always areas to improve, and so for future work, we want to fix our physical mechanism. Currently, it also interferes with proximity sensors, so we can't use the full range of motion with the dog. It's not able to walk backwards, and the load-bearing joint the joint cracked because it's not load-bearing enough. You can see in the bottom right image, it cracked twice in the same spot. So we're gonna CNC our part so it's made of metal and a lot more durable. In addition, Spot's walking capabilities are inherently limited to 3 meters. So if you saw in the video, it would walk 3 meters, then stop, and then continue to do this. And while it's effective, it's inefficient. And so finding a way to work around this and prevent that using the autonomous features is something we want to work on. And then next is training the model on other trash types. We noticed that aluminum cans are within the top 10 most littered item on the Jersey shores, but expanding this to something like plastic or glass will really round out our project. And it's worth noting that we're not looking for short-term gains. We're building our solution for long-term impact and to be scalable because it's reducing physical labor, preventing exposure to pollutants, creating data-driven insights, and facilitating benchmarks for municipalities to use across multiple years. Really, we're redefining beach cleanup for the future. Thank you.
So you have Spot, he's here, right, to use them. So I saw your test site is a volleyball court, right? So lots of people walking on it, reasonably flat. Have you actually taken Spot down to the Jersey Shore? Because there, it's not flat. There's angle, there's movements, there's impact of wind. You know, Spot is inherently unstable when he actually gets on terrain which isn't pretty flat. So why Spot versus, you know, a 4-wheel drive, RC, you know, an all-terrain sort of approach? Why do you use Spot?
Yeah, that's a good question. First, to answer your first part about taking it to the beach versus the sand courts, I think we noticed that the conditions at the sand court were surprisingly similar to the beach. There were not as many footsteps as we expected. We tested on empty courts most of the time, so it wasn't flat. And then why we didn't use something like a 4-wheel mechanism, like you said, we wanted to use Spot because we were able to do a more targeted approach and actually pinpoint where the trash is. We saw other competitors are using rakes that kind of almost like a Roomba for the beach, and so they'll scan a wide breadth of area, but it's not targeting specific locations for the beach, so it's inefficient in terms of time. So Spot is really good at walking towards its target, walking on the terrain effectively because it does have auto balancing, and then it's able to pick it up successfully. And it's faster than other mechanisms that we were looking at as well.
And what was the challenge, and why couldn't you, a different approach would be Spot actually having access to the GPS data, right?
Mhm.
So rather than, you know, you're supposed to have an interchange there where you're actually taking the information from the drone, taking the GPS locations, and then doing, why haven't you, or have you thought about taking Spot and actually tying GPS to Spot?
So we tried tying GPS into Spot, but because of the inaccuracies of the actual GPS module, we weren't able to get Spot like at the right point there's just too much variation based on the GPS, the locations that the drone calculated versus where where Spot would actually go, and then Spot does have GPS compatibility, but a lot of those GPSs are upwards to $10,000. So it was just out of our price range.
Just to add on to that, in terms of like standard deviation of what we're looking at, the cans are so small that we have to be within like 1 meter apart, and the coordinates that we're using are from 5 to 10 meters up in the air. So it's bound to have inaccuracies if we're using 2 GPS sensors. So using like one sensor along with trajectory commands really minimizes the amount of error that we're getting.
Yeah, this is a great idea. I think it'll evolve, right? Once the technology evolves and allows you to combine the drone with the dog, I think then it's going to be a much better product. This is nice to be able to start out thinking about stuff like this, because this is where it has to go, right?
Mhm.
Did a good job. I also like the Blues Brothers.
Thank you. Yeah.
Thank you. Appreciate
Get a
it.
match for the occasion. Yeah. Yeah, bathing suits would have been more fitting.
Bathing suits.
Yeah. Thank you.
Thank you.
Appreciate it.
It's down. There. Yeah, the Google Slides.
This one.
Yes.
Have fun. Everything works.
Okay, good morning, everyone. We're Group 13, and we're Mindful Learning. So my name is Alyssa, and my teammates are Bina and Charmine. And first, we'd like to give a special thank you to Dr. Aziz for helping us out on our project. He was our mentor throughout this. So here's a quick overview of our project and the topics that we will be going over today. And first, I'd like to get into the problem statement. So we're college students, and it can be stressful to be studying. So we want to analyze and find how stressful you can get and how that can impact your physical and mental health. This problem highlights the need to identify stressful study methods for each individual specifically. So we have a hypothesis that we want to find the body stress response with varying study techniques. We're going to be using different variables which will output if the study technique was stressful to the student. So here's a quick demo of what our project looked like. We have 3 inputs, which is essentially an eye tracker, and then we have a graph in the middle here, which is measuring skin conductance, which high and low is like the varying skin temperature, and then we have heart rate, BPM, and then that outputs a binary of stress and no stress. So what's our solution? Our solution is to provide research that analyzes the stress levels in these students so that we can figure out which study technique could be causing the most stress in real-world education scenario. As for the technology, the hardware that we use is a pulse monitor, which is plugged into the ear, as you can see on the right photo. We then have a galvanic skin response sensor, which is a GSR, which is shown on the 2 fingers. And then we have a gaze point eye tracker, which is shown in the top left, which takes a video of your face and detects your eyes. As for the software we use gaze point analysis to collect the eye tracking data, and we have processing environments that collect the GSR and pulse monitor data that outputs into Excel, and then we run the code through Google Colab.
Now moving on to our methodology. So this is a brief flow of what each participant went through. So we started collecting the data, and they had a relaxation period to bring them down to baseline because everyone has different stress levels. And then during the testing duration, we decided to test them on content based off of our course, Engineering Statistics, because our demographic all had taken that course prior. And towards the end of our experiment, we decided to implement a NASA task load index test, so we were able to see how they felt when they were taking our test. The 2 study techniques that we implemented were active recall and self-explanation. For active recall, it focused on memory retrieval, which can induce stress from the difficulty of recalling information. So for this, our participants were not able to reference the material that they had studied, and they were answering these questions based off of their memory. For self-explanation, it focused on articulating their understanding, which can cause stress because of the cognitive load when it comes to explaining. So for this, the participants were able to look at the material while they were answering the questions. So as you see below, there's another flow diagram which shows that the 4 runs that we implemented in our test. And these runs were randomized to reduce any biases when we were having them go through each of the study techniques. We chose to do a fractional factorial design. Because stress is so dynamic, we implemented 3 different conditions: studying technique, difficulty, and music or no music. Along with this, we chose a fractional factorial design because it significantly reduced the number of runs. If we hadn't done this design, it would cause many runs, which caused fatigue for the participant, which you wanted to account for. So for the analysis of the data that was outputted from the 3 sensors, we first pre-processed it, and then we compared each run data to their initial baseline data. As mentioned before, we showed them a video to bring them down to baseline, just to identify what each individual participant's baseline stress level was. Then we performed statistical tests, and then we concluded which studying technique each participant chose as their stressful one. To reiterate the inputs and outputs of our design, for the GSR, it conducts the skin conductance, whether your skin gets sweaty, whether it heats up. Then for pulse monitor, that's for heart rate. And eye tracking has pupil dilation, fixation, and moving gaze. And then the output conducts a statistical test, which I'll go into, to basically conclude whether it's stressful or not stressful. So these are some of the pre-processing techniques that we used for each sensor, and the statistical model that we decided to go with was Welch's t-test. So just to go into this, if the p-value was below 0.05, this showed that there was a statistically significant difference and that studying technique caused stress. However, if both study techniques had a p-value below 0.05, we moved on to looking at the absolute value of the t-statistic, and whichever absolute value was greater, that proved that study technique was the most stressful. We also, in order to standardize our study further, we decided to look at if 2 out of the 3 sensor readings agreed, then that study technique was the most stressful.
So these are the results from participant 2's data. On the graphs on the left are the 3 different eye tracking variables, and in between the same colored bars represent each run. So for example, on the top graph, in between both the purple bars is the first run, and then any peaks in the graph represent high stress. So for this participant, runs 2 and 3 represented active recall, and runs 1 and 4 were self-explanation. So after we did our analysis, we saw that the p-values were under 0.05 for both studying techniques. So then we moved on to the absolute value of the t-statistic, and in this case, active recall caused them more stress. So now looking at GSR and heart rate, for the p-values for self-explanation for both sensors, they were greater than 0.05, so then we can automatically deduct that active recall caused them more stress. So for this participant, all 3 sensors showed that active recall caused them more stress. So for our testing and validation, our goal was to measure the reliability of our experiment, and to do this, we used the NASA TLX questionnaire. So the participants were given a question at the end of their testing experience to rate how stressed they felt during both active recall and self-explanation. And then we're going to use the data that they get rating their experience to the data we collected with their sensors. Below is just a picture of how the test looks like. So this is a summary of the testing and validation chart of what result they felt the most stressed for versus what our sensor said. And as you can see, only 2 participants did not have a significant amount of stress from our sensors to say which studying technique made them more stressed. So to summarize our results, 82% of our results were consistent with our hypothesis. So we can say that the stress levels in participants did favor one study technique over the other. Therefore, we can accept our hypothesis. So for our value proposition to link everything back together, an application of our research will allow for more individualized feedback so that students can gain better insight on which techniques allow for better comprehension and less stress.
As for our contribution, stress is very dynamic, so we came up with different runs that would create a variability. And then also, this project can be scalable for broader applications in other industries like the medical field for therapists to use on participants. Thank you, and any questions?
For each participant, we did 4 runs because that was what we came up with our design of experiments. And then if you're asking for how many participants, we did 11 participants in total.
And so from that data set, what was your primary conclusion? That active was a more stressful way of...
So the conclusion of our study wasn't necessarily to choose one study technique over the other. It was just to see if the system that we created, by analyzing the data using statistical analysis, we could identify that the results that the students thought that they felt stressed during a specific study technique, our results matched those. So kind of to see the consistency of those results.
Okay. And I'm just trying to understand what the practical value of this to a student would be.
So what we want to do for future application is to make a product that would essentially help students identify what study technique causes the most stress for them specifically. As stress is so dynamic, every student is different, so it's more to identify like what causes them the most impact.
And not only that, when a student is experiencing stress, they might choose study techniques that they don't even know is causing them stress. And they might think, okay, active recall is the best way for me to study, but they're not understanding what they're studying. They're not being able to understand the content that they're studying, because it is proven that when you are stressed while studying, you're not being able to retain the information, and you're not going to be able to perform as well as you would expect on your exams.
Could you give like 3 examples of different types of study?
Like study techniques?
Yes.
Yeah. So one of them would be, I guess, active recall self-explanation is what we already did. Another one would be repetition. So that would be one. Another one was Pomodoro effect. And then the third one would probably be like Quizlet, where they constantly are looking at flashcards. So we chose the two that I guess were kind of similar but also opposite, just so we could see what students liked the best.
I see clinical application here. I mean, what do students do today when their parents maybe, or maybe themselves, they sort of notice that they're getting stressed out when they study? I mean, I'm having a hard time relating, because when I studied too much, my face would fall into the book and I would stop breathing. So I kind of knew that I was probably studying too long. And what do students do today? Do they go to the doctor, and do they try to get diagnosed?
Right, so probably not. I mean, when people get stressed out, they probably go take a walk or go take a break. And I mean, we're not trying to get rid of the fact that everyone needs a break while studying, but we're just trying to kind of be proactive and kind of take a look at mental health and physical health when it comes to applying it in an educational field, because we can often get caught up with studying, doing work, and not really understand the adverse effects it can have on our body as a whole.
Just to know the different reactions of organism may take different time. Just to know. So it's like your eyes may react different, like
right.
10 seconds, but resistance of the skin may be like immediate.
Yeah. So that's why we decided to implement multiple sensors, because we realized that there are so many inconsistencies if you just use one. So we decided to use 3 just to validate our study even more. Thank you.
All right, hello everyone. Today we're going to be presenting on the NGBot.
I'm Allie.
My name's Yash,
And my name's Thunby.
and we'd like to do a huge shout out to 3 people that really played a huge part in our project. The next one. Sorry. So we found a problem. Many universities lack the immediate ability to answer major specific academic planning questions accurately without the use of deans and advisors. And to combat this, our solution is to create an interactive model, which is the chatbot we have developed, which provides 24/7 answers to academic queries in order to improve accessibility and decrease stress in students that are planning their college curricula. And our proof of concept is we developed a chatbot for the School of Engineering, specifically for the Industrial and Systems Engineering department. So here we have a video that kind of showcases when it's a visual representation of how our integration works with our chatbot. So we can ask it questions such as, give me a description about courses, tell me a little bit about industrial engineering as a whole. What clubs and organizations can I find at the ISE department at Rutgers? What are some of the prereqs for a lot of the classes that I'm interested in taking future on? And it's very heavily involved in curricular planning. A lot of students come into the School of Engineering already completing courses at their transfer colleges or even from advanced placement classes they've had through high school. And it's not always easy to kind of navigate your own career in college. So this chatbot makes it much more easy for you to figure out what classes you need to take based on the input that you give it. And to further the example, so let's talk about some of the resources that are currently available to students. Live chat is the one that Rutgers School of Engineering already provides. However, there's many limitations with this. Students can only access it during certain times during the day and certain days during the week. And that requires a student worker on the other side to be controlling it and responding to your prompts and questions at the best of their ability. ChatGPT, we all know ChatGPT, right? We ask our general questions to it, but you can only get general answers through it, not specifically for Rutgers ISE. And then academic advisors, great tool. However, they're not always available. Think about when we're trying to make our schedule at the beginning of the semester. Hundreds of kids trying to meet with one advisor, very difficult, not easily accessible. Where our NGBot outweighs the other competition is through its accessibility in those three categories. So here's another example to kind of show it, our NGBot compared to ChatGPT's responses. We have a question here about economics and give us courses that are available in the ISE department. It accurately gives us those accurate electives that students can take, while ChatGPT, on the other hand, will give you general ones, and none of those courses there are even offered at the school, even though we specifically indicated we wanted it for Rutgers ISE. And I already kind of spoke a little bit about for curricular planning. So here's another example where a student came into the School of Engineering with already some classes they've completed, and it's able to answer that based on changing up their schedule and tweaking it in terms of what they've already taken, while ChatGPT struggled with that.
So next I'll dive into a little more about the methodology, starting with large language models and our choice of llama. So what exactly is a large language model? It is a system trained on large corpus to process and generate text clearly. And this contains an X number of parameters, which are the weights and biases within the neural network layers. So llama is a autoregressive language model, and this means that it is asked to predict future tokens, so characters or character sets, based on previous tokens. So this is ideal for text generation. And the three main reasonings behind choosing llama is that it's an open source model, it's decoder only, and it benefits from efficiency versus size. So since it's an open source model, it's highly accessible for people to use. Because it's decoder only, it's designed for generating text, and it's very flexible in handling diverse inputs. And with its efficiency versus size, we use the 3 billion parameter model. And while this is fewer than other choices out there, and it makes it less resource intensive, it still has a high performance and provides comparable results. So this is just some of the technology and tools that we use for programming, natural language processing, and fine-tuning, including the Llama 3.23 billion parameter model, and as well as other important frameworks and libraries such as Unsloth and Transformers. Now I'll give an overview of our process flow, which shows the framework for our code, which starts with importing the libraries and configuring the environment, importing our CSV data file, which has the questions and answers to train the model, and then we split it into the test, training, validation sets, load the model in the tokenizer, and convert it into the parameter-efficient fine-tuning version. From there, we can configure the hyperparameters to set it up for training and actually train and fine-tune the model. And depending on if it performs accurately, if not, we can go back and reconfigure the hyperparameters, and if it performs accurately, we can save the finished fine-tuned model.
So onto testing and validation. So for testing and validation, we did a local testing on Google Colab where we input a variety of different questions and allowed the users to judge the accuracy and clarity based on the response. As mentioned before, we did use a CSV file full of data, and that data was from the ISE handbook. We also did splitting data, so we created a test, validation, and training set to ensure the model generalizes well to unseen data. And with that, we also did a loss comparison where it also compared the training and validation loss to show the model's ability to, again, generalize with decreasing validation loss indicating a better performance. So on the left here is a visualization of the training and validation loss from one of our first fine-tuned models. As you can see, they are very far apart with the validation loss kind of plateauing and then the training loss decreasing rapidly with a lot of fluctuation. This can show overfitting. And then on the right here shows our current training and validation loss. The lines are very close together, not far apart, which shows that our model is generalizing very well. So for our value proposition, some benefits are academic benefits, including immediate 24/7 assistance. As mentioned, it's very hard to get advising appointments, especially around course registration. So this is a very big plus to our chatbot. And additionally, this also provides a pipeline for a chatbot for other majors at Rutgers or other schools outside of Rutgers. And additionally, health benefits. Proper advising can lead to reduced stress and anxiety and also improve mental health and well-being. And with that comes our system contributions. Again, we fine-tuned Llama Model 3.2 and adjusted the hyperparameters to optimize its performance and the scalability. Universities can input their own data and create their own chatbot based off of what we created. And with that being said, thank you. Any questions?
You're going to ruin Rutgers' reputation for being difficult to navigate. It's data in, data out, right? It's good data in, gives you better result out. So where's your data coming from, and how do you know you have all of it? Like, during your testing, were you able to uncover questions that it couldn't ask and then refine the model through training?
Yeah, so our data came from the Rutgers ISE handbook. Training a model to create a chatbot takes a lot of time, so we decided to start on a smaller scale. So we did use the information from the ISE handbook, and we made sure that all of that information was within the CSV file.
And was it enough?
Yeah.
Gave you everything you needed?
Yeah, to answer. Yeah. For
To a general answer, I would imagine, if you couldn't give you a specific one. If somebody gave it a question that the detail wasn't available.
Yeah, so within the CSV file, we input questions to train it on information it might not have to show that if it's outside of the scope of what is in the ISE handbook, it'll answer like, I don't know, or I don't have enough information for that.
And then you train it, and then you get that data, right?
Yeah.
Correct.
I'd be curious at some point to sit down with an advisor, an academic advisor, have your questions, have the advisor answer the questions, and then compare them to actually what you developed in the model. Have you done that, or have you?
We have not. But that's actually a great idea, and honestly, like, it'd be honestly like a great test to kind of exactly.
That's proof of
It's
concept
validation
right
in itself, exactly.
Yeah, we kind of used our schedules. Like, I know Ali switched into ISE, and so she met with Dr. Wicks prior to coming into the major. And I remember, like, freshman year when I met with my advisor, and they gave me recommendations based on what I completed. So we kind of worked on also asking those questions to see if it aligned with, like, our specific schedules and recommendations that were previously made.
I mean, in many ways, if this, as you said, it's very difficult to get appointments, especially at the beginning of the semester. So this could be implemented, many of the sort of, separate the wheat from the chaff. All the basic questions can be moved to the side. A really difficult question, you have the advisors doing things where they really add value.
Yeah.
That's great.
100%. Thank you. Yeah. Sorry. Yeah.
Make feedback from users saying this professor is great. This
Thank you.
Remember, like when you play it, it's right here.
Oh, so I'm starting with this switch. Oh, yeah, right. Thank you.
It all comes down to Jersey tomatoes.
Always does. All right, hello everyone. We are Group 8, and our project is Guardrone, a fungal detection tool. I'm Luke Tharney.
I'm Chelsea Obade.
I'm Timothy Price.
And first, we want to give a special thanks to Professor Peter Nish and Professor Andy Wynat from the Scientific Research Forum for allowing us to use their land, as well as Maxine Marvosa at Rutgers Gardens for the same reason, and the Rutgers Master Gardeners for connecting the dots logistically for us, and finally, our technician Max Powers for drone help. This is our agenda for the day, as you can see. So what is the problem we're trying to achieve, or trying to solve here? So we are trying to target small and medium-sized farmers who do not have proper or sufficient access to advanced fungal detection technology. Now, why is this? Commercial solutions do exist, but they're largely made or designed for large-scale farms, and they're also too expensive. A lot of these programs require specialized imagery equipment for them to work. And the traditional methods, apart from the advanced technology side, are too time and labor intensive as they are. So what is our solution? We have decided to create a user-friendly and affordable software program that hits these key features. We want to be able to detect fungal infections and differentiate healthy and infected crops. We want our program to be able to integrate with a drone, and we want to be able to do spot and batch processing, and we want it to be scalable and time efficient as well. And this is our demonstration. I'm a little old-fashioned here with the URL. There we go. So as you can see here, this is our dashboard. This is what the customer will see from their perspective. So you go and you drop and add a file, and these are drone images that we collected ourselves out in the field at Snyder Research Farm. In terms of data collection, we kind of got hit hard a little bit because there was an early frost and the conditions were really dry, which limits the ability that you can detect fungal images. But as you can see here, we did manage to get some images like this. These images contain both tomatoes and pumpkins, and then when you launch the results, it gives you all the instances that it detects of the fungus, and it assigns a class, and the numbers on the right are the classes, and then the confidence intervals, and those classes are numbers that are assigned to a specific vegetable type. So for example, a 0 would be a unripe tomato, a 1 would be a ripe tomato, a 2 would be a pumpkin with fungus, and a 4 is a pumpkin without fungus.
Wix Studio and Pantone present.
All right.
Now that you have seen how our product is used, it is important to understand the behind-the-scenes mechanics that make it all come together. Next slide. Drone capture is fed into the guard drone detection program alongside a weight file, similar to a reference sheet. It outputs any identifications as to fungi, where in the image they were detected, and the confidence level associated with the prediction.
So on the back end of our project, we used a software called RoboFlow. It is an open source platform that offers tools to help developers create and deploy computer vision. On the right, you could see the class names that we mentioned in the demo. We then fed images collected from the internet into RoboFlow, which we used to annotate and feed into our training model. The figure below shows the data splits.
To that end, this is the core of our model, or as Dr. Jafari likes to say, the meat. The model intakes an input image at different scales, and it cuts them into different pieces. It'll stack these together in different combinations and send them through the head of the model where the actual classification takes place. We can host this YOLO v5 model on a Python notebook thanks to the Ultralytics package, which is a Python package that is analogous to PyTorch or Keras, which significantly reduces the need for repetitive lines of code.
So now continuing on to training and testing, I'm going to take you through the 4 key steps of training our model. We begin with the aforementioned annotation of our classes. We then move on to loading this data into the YAML file. This contains information on the training and validation directories, as well as the class names and the number of classes. We then use the Ultralytics package to train our model based on the YOLO v5 architecture. And finally, the performance metrics are logged into TensorFlow. So I'm going to show the visualizations of these performance metrics. So accuracy is plotted here using the MAP_0.5. And as you can see, we have scores going upwards of 72%. And next is precision, and this tells us how well our bounding boxes or annotations are detecting the plant classes we've created. And as you can see, the scores are upwards of 70%. And finally, recall, which is a very important metric because when we train our model, we use pre-annotated images. This tells us how well our model works on unannotated or random images, and the scores, again, are upwards of 70%.
Now just to give a little more insight on our value proposition and what our contribution to the project is. So what is the significance of guard drone It is a viable solution for smaller scale farmers to meet their plant health and analysis needs. Now, when I say these small farmers, I could mean farm owners who provide for their family, food for their family. This could also mean research farmers for educational purposes. This helps bridge the gap between those smaller scale farmers and the commercial farmers' capabilities in terms of plant health. Then, time, labor, and cost-efficient solution to fungal detection, and it has a simple user interface for ease of use. Now, what makes our implementation unique? Fungal infection detection is the central focus of our project. Computer vision is implemented for fast, reliable results, and is largely scalable for many different plant types and geographic regions. This could be used anywhere around the world where these plants are planted, and it could be used for any type of plant. We have only done it on tomatoes, pumpkins, and eggplants thus far, but it can be replicated for more. Thank you.
Thank you.
So now I am a farmer. I actually am a farmer. I am a farmer and CEO of Amazon and all of those.
Amazing.
But, so one of the questions would be, so when you're farming, right, you want early detection of problems, not late detection of problems, right?
Right.
You want to actually solve the problem before it gets bad.
Right.
And so one of the questions would be, can you create different classes of, so a totally healthy tomato versus a tomato which is just sort of showing some signs versus a tomato which is rotten and has been completely fungal.
Right. That is totally within our means to be able to do that. Yes.
That again, if you're sort of you want to take proactive steps as opposed to reactive steps.
Right.
You wanna,
Exactly.
As a farmer, you want to actually solve the problem before it becomes a problem.
Right.
You want to catch it early. So if that would be something that if you could do, I would be curious about that. Then the other part is, so I get this data, and now I'm a small farmer. How do I use the data, right? I mean, so I have a problem out in my field, right? I mean, what is the value prop of this? Is it you can catch things early, you can take corrective actions, or this year my yield on my crops I lost 50% to some fungus. I mean, to me, the value is if you can take steps to fix the problem before it becomes a real problem.
Yes, that's actually a very good question. That is in our future work because during our research, we did have solutions to eliminate or mitigate the fungal infections, but we didn't get the time to integrate that into our user interface.
And again, as a farmer, right, and you'd find is typically you find fungal infections or things that actually are impacting your crops. They oftentimes they affect the entire crop, or they're in particular areas of your field, right? An area of low lying where water has collected and plants begin to rot or get fungus. And the idea here would be if you could sort of provide some type of mapping of your farm, your field, and say, okay, in this quadrant here, you are having a real fungal problem. Get out there quickly and take proactive steps.
Yep.
You know.
Yeah, we originally when we were just sort of bouncing around ideas, that was definitely in the topic of conversation. It just happened that it was a little bit out of our range as per the time frame that we had. And another solution to that could also be taking image numbers and knowing the distance between shots of your image, and then figuring out where in the field it is based off of that. That's another possible solution as well, as a more concrete solution that's not necessarily GPS oriented. You know what I mean?
Is this also something that you could do as a subscription service?
Yes, lots of items on the market that are usually commercially oriented do have subscription services. That's for ones that are
You'll fly the
out.
field and
Right.
That's where the money is, right? You want somebody to sign up for the long term, and they're
Right.
paying you every month versus having them buy a drone, them a one-time, fee for your.
Right, so they send it out.
Right.
Right.
You want to keep them as customers over the years, and as your product evolves, they evolve with it. It gets
Right.
better.
For sure.
And you may collaborate with one of previous projects of short cleaning. So this robot may come and pick this rotten tomato.
Right.
For sure.
Yes, for sure. We'll let you know on that. Thank you.
Well, do we get a star?
23 hours. Thank you so much. We are on time. Now, from this point on, lunch will be served soon. We'll take you to, it's in the lab area for the